So we're going to talk about limits, which might be a strange thing to talk about because, well, you already probably, if you're watching this video at least, understand limits in the most important and basic sense. So it might feel like a strange thing to come back to, and I will completely confess that this will feel like a strange thing to come back to in AP Calculus because it's not an AP topic. Having said that, it was a topic that was a part of our limits unit for years. I think the last year we taught it this way was 2017. Maybe it was 2016. I might be off by a year. And basically, we led things off, not the first day, but in that first unit, we closed it out by coming back to our definitional limits and talking about, like, well, what does this mean in a rigorous sense? Meaning, how can we formally define a limit? Because although you might have just sort of bought it hook, line, and sinker when I introduced it on the first day, there's some ambiguity around our definition. There's some imprecision that's there, and we want to address that formally with a process called the Epsilon-Delta limit proof. A process. We want to prove these limits rigorously, and we're going to do that with something called Epsilon-Delta. So in here, where I wanted to begin our quick little lesson here, and it's going to consist of some definitions, some thought experiments and discussion at the beginning, and then a couple examples, including one that's a little more challenging involving a quadratic. Basically, I want to start by going back to the definitional limit that I've been using for the last couple years, which is what you see on the screen right now. It says that a limit is a quantifiable description of the general behavior of a function around a given x value. And this is a good definition. It points to a lot of different things, like the behavior of a function points to the fact that there's a y value sort of thing happening here. The value of a limit is a potential y value. It's not the exact y value necessarily, but it's a y value. It's around a given x value, so there's some connection between x and y. You'll sometimes hear the word neighborhood put in here as well. But there's a lot of ambiguity here. There's a lot of uncertainty, and there's a lot of things in this definition that just aren't very rigorous. Like, for instance, I'll point out both of the phrases that I think are really there. Quantifiable, sure, it just means your answer is a number. Like, we're aiming to answer with something that's a number. But the two things that I think are most sort of awkward here from a mathematical standpoint, and remember, part of mathematics is axiomatic. It's trying to get things down to a definition saying, based on this system, this is how we define this. What's general behavior? I mean, I know it opens up all sorts of possibilities for me to make jokes about military ranks and like, well, it's a little bit higher in the pecking order than a colonel behavior, but those jokes are mediocre at best. And also, what is general behavior? Like, what does general mean in this sense? There's no indication of what it is we're looking for here. Is general like within a certain frame? Is it like a description of behavior from two directions? Like, we interpret it that way, but what does that really mean? We don't actually have a good definition for it. And then the second thing in here that points to that sort of awkwardness is this word around. And in the past, I've used definitions. I've got one pulled up on the other screen here, just to kind of keep me on track. I called it like the general behavior as we approach a given x value. Well, here I use the word around. What does around mean? It's kind of like if someone asks you where you're from. You know, if they're from Lodi, you probably tell them you're from Elk Grove. But if they're from Southern California, you probably say you're from Sacramento. If they're from Baltimore, Maryland, you might say that you're from Northern California or just California. Around can mean a lot of different things. Like, oh, where are you from? Well, I don't know. In the future, who knows? Maybe around could be, oh, I'm pretty close to the sun. Who knows? So basically, there's some imprecision there. So part of the goal of what we're looking for in this lesson is a way to formalize those terms. To avoid that sort of hand-wavy, touchy-feely general behavior, around, near, neighborhood, approaches. These are all mathematical ideas. They're conceptually accurate words, but they're not precise. So we want a precise definition of what it means for a limit to exist. So in a sense, what we're going to do is we're going to attack the notation of a limit and break it down in a different way. And I'm not going to go into the deep history of this like notation or anything like that. I'm just going to point out that what we're trying to show here is that the limit as x approaches c of some function f of x equals L, and we are going to assume in all of the proofs we look at here that L is a real number. So we're not looking at the infinity situation. That doesn't come up in the work that we're doing here, and I've actually never run into a formal proof of that. If there's time at the end, if this hasn't run long, I might mention epsilon m proofs, which have to do with limits at infinity. But for us, every limit we look at today is going to be a finite value. So the question is, that's our notation. That's our idea up at the top in my definition. In fact, I notice in my work over on the side, I literally have quotes on here. I say I have air quotes, but that's just not true. Like, air quotes would not be on the paper. Some pretty nice quotation marks. But we don't have a formal definition, so we're going to formally define it. So if you want to know what this really means, and you can tell this is going to be a little bit of something coming because I've used different colors for all of the pieces here, the limit as x approaches c of f of x equals L means for every epsilon greater than 0, there exists a delta greater than 0, such that if the distance between x and c, that is, by the way, the absolute value of x minus c, is less than delta, then the absolute value of f of x minus L, or the distance between f of x and L, is less than epsilon. And what you're seeing here is an attempt to create a formal connection between what we mean to be closeness in x with closeness in y. That is our goal. And the little translation I offer in purple down below it is, I think, a good description of it. This was a new addition here. What we're looking to do here is establish a formal connection between the nearness of x to c, as in the closeness of a given x value to the value we're interested in computing the limit at, to the nearness of the function, or the y values, to that value L. And that's a lot. Like, that is a lot. Although I do want to point out that the biggest idea here that I think is worth sort of establishing is that this represents a distance. So we're trying to limit, we're trying to restrict, there, we'll use restrict so as not to confuse things here. We're trying to restrict how far away an x value can be from that value c where we're computing the limit. And we're saying that they are distance of delta away from c. And what we're saying is if that's true, then our limit is always going to be within some other related number, epsilon, of the limit value. So in other words, a closeness in x leads to a closeness in y. And in particular, there is a formal connection between delta and epsilon. That's why these are called Epsilon-Delta proofs, because we're going to use epsilon and delta to represent those tiny distances from the x value we're interested in and the y value we're interested in, aka the limit. So I don't want to just leave you there. I want to kind of establish what this looks like and kind of give you an idea of the picture. And then we'll do one of these proofs before I talk about the plan and show you exactly what's happening. And at least in a linear situation, I think I can make it pretty clear what's happening. But this is more a process. I think when you first start this out, it's less I understand every single nitpick here, exactly what's going on. You get used to the language of it. You get used to thinking about the idea that there is a formal connection between these two things. I would say if we were looking for this, I'd look for you to get comfortable with the proof structure. I'd look for you to get comfortable with this idea of closeness in x being related to closeness in y. But to help you with that, let's take a look at what's happening here. So I have the same definition and the same little elaboration or translation right below it, and I've sketched out a curved function f of x, and I have established for us on there, although I didn't do a good job of sketching it out so you kind of see, I have x equals c, and then very conveniently along this horizontal line, I have y equals L. So basically we can kind of see that point right there that we're looking at, that point, the hole, and it can be a hole or it can be a full point, whatever it is, that's the point C comma L. It just happens to be a hole in this picture, sort of for general purposes. So now, what is it that we are establishing here? Because I think that's sort of a helpful thing, is to get a graphical sense of this. I think you have it sort of verbally at this point. Let's get a graphical sense. And by the way, if at any point I look uncomfortable, it's because it's 103 outside, and this room that I have has no fan, and there's a big old window right there that makes this room unbelievably warm. So I apologize. If I start having little beads of sweat, my bad. There's a limit to how far I can go in this lesson. So in any event, we've got this established connection. We're saying that if you are within this distance of C, your function values are going to be within this distance of L. So let's show you what that ends up looking like. So first of all, let's just establish a delta. I'm going to say that delta is the distance from right here to here. So in other words, this little distance from the red line to there will be delta. So that is delta. And delta is just a fancy D. Sometimes I think of it as a musical note someone's hanging on a Christmas tree. I don't know. So that's going to be delta. And then, of course, it's going to be the same distance in the other direction as well. So that's delta. What that establishes is an interval of x values. Basically, on the far right, we would be at the point C plus delta. And on the far left, we would be at C minus delta. Now, what that does is it establishes sort of a window, almost a range of values that we can consider here on our original function to establish that closeness. So according to this, if our x values are within that range, and by the way, maybe it's worth pointing out that if you have x minus c is less than delta, that's the same thing as saying x minus c is less than delta, but also greater than negative delta, which is where c minus delta less than x less than c plus delta comes from. So just FYI, that's why our interval down there is what you see. Now, having said that, though, as soon as we set that piece up, we also can deal with the sort of result. Like, what is this telling us about the values of the function? Well, they're within epsilon of our limit value. So if I actually sketch this out here, I'm going to draw these lines over here. And because it's curved, it's not going to be quite as clear as you might want it to be. But it does a pretty good job all the same. So I didn't do a perfect job. But basically, in a sense, we're going to end up with a range of values for the limit, the function as well. And in fact, what's happening here is we're sort of boxing it in. And again, there are some issues here with epsilon. If you're looking going, those aren't the same. Yeah, I know. There's some issues here because this is curved. We'll look at linear ones first just to kind of establish it. But basically what we're doing is we're sort of honing in on the curve and saying effectively what we can see is that all of our y values have to be within this distance of our limits value. That would establish what we're looking for. It's basically if we are within delta of c, if our x values are within delta of c, then our y values are within epsilon of L. And that's how we can formalize the connection. Because if you make d bigger, delta bigger, if you decide instead, and I'll just do some really large, colorful things here. If you decide to make delta larger and you're like, oh no, this is my delta. I believe in big delta. Oh, ho, ho. Yeah, that's sure. Okay, I don't know where that voice came from. But you get the idea. Then what happens is, of course, epsilon's going to get bigger as well. All of a sudden, you're further away from the limit value, so you just have kind of L plus a bigger epsilon, and L minus that bigger epsilon. You just sort of increase the range. The further you are away from C in the x direction, the further away in y you end up being in the y or further away you end up being from L in the y direction. So that is our formal connection. We are trying to say closeness to C implies closeness to L. You might even I almost want to say that they're directly proportional, but I don't want to say that for sure. I'd say that they are proportional. Like there's a proportionality to this, just in the sense of conceptually as one gets bigger, the other gets bigger, as one gets smaller, the other gets smaller. But there's your general idea. And that little boxed in idea there, we will actually look at when we do a limit. When we do a limit that's linear, because linear does a really nice job of illustrating this. Now I said we're going to be doing proofs. That usually turns people away from the process completely. But really these epsilon-delta proofs look really intimidating, what with all their Greek letters, but they're actually really trivial to do. I can't think of a better way to describe it than just that. They're really trivial to do once you're there. So we're going to do a full proof. I'm going to do the process. I'll show you the full process of where it works, like what your work looks like, what your kind of like prep work looks like, and then we'll do a proof. Then we'll talk about it, formalize it, do one more, and then I'll go on and show you kind of the tricky situation and call it a day. It's been a warm day for me here. So in any event, what we've got here is we are told to prove. Ooh, it's not just evaluate, because it's already evaluated for you. Nice try. We're supposed to prove that the limit as x goes to 3 of 2x minus 5, a nice classic line with slope 2 and y-intercept negative 5, is equal to 1. And if in your mind you're like, oh, sorry, it's a 3. I was going to say, wait, that doesn't work. Yeah, that's equal to 1. Or if you're like, but like lines are continuous. Yeah, I know. I know this is obvious that this is true. But just because it's obviously true and because we have other approaches doesn't mean that it's been formally proven. Limit is sort of a non-rigorous, imprecise tool until we establish this formal connection between closeness in those two directions. So here's what we're going to do when we go to do this proof. We are going to, in a sense, reverse engineer a value of delta that depends on epsilon. And our reasoning for that, I'll say that one more time. We are going to reverse engineer a value of delta, delta being the distance you have to be from the c value, the x value we're interested in. We're going to reverse engineer a delta from our epsilon, which is how far we want to be in the y direction from L. And when we do that, we will formally establish the connection. We'll end up with a result that shows delta as a function of epsilon, meaning that delta, our x distance, and our y distance, epsilon, are connected together. So work backwards and then prove it in the reverse direction. So we literally do begin, by the way, with like literal work. So it's kind of like you begin with work and then basically off to the side after a little bit of time, we will go forward and then we will begin the actual proof. So we just do a little bit of work first. And in a sense, that work is really important because it's going to establish the connection between delta and epsilon. We got to establish our connection between closeness in x, delta, and closeness in y, epsilon. So there we go. So here's where we're going to begin. We're going to start with the end in mind. We're going to begin at the absolute value of f of x minus l is less than epsilon. That's our first move. That's where we want to end up anyway, so let's just make sure it's going to be true. Now, of course, in our limit up here, we can establish some important pieces. F of x is clearly going to be that line, 2x minus 5. You have c, you can. C is equal to 3. And of course, our limit value is equal to 1. So those are all of our ingredients. In addition to my computer starting to struggle because the internet is going out, basically we can establish 2x minus 5 minus our L value 1 is going to be less than epsilon. So I've just plugged some pieces in. Doesn't seem like I've done much, but bear with me. So from here, if 2x minus 5 minus 1's absolute value is less than epsilon, well, that's clearly the same thing as 2x minus 6's absolute value being less than epsilon. And then, of course, you're just looking at it, I can go ahead and factor out a 2 from that. So there's our stuff. Now, this is a little weird the first couple times you do this, and absolute value sometimes has some weird conceptual things in people's minds, but the absolute value of 2 is just 2, so I can literally factor out just a factor of 2, and leave us just 2 times the absolute value of x minus 3 is less than epsilon. Finally, I'm going to get x minus 3 alone. It might seem arbitrary for a second, but bear with me. I'm going to divide both sides by 2, and I'm going to get that absolute value of x minus 3 is less than epsilon divided by 2. Now, what have I accomplished? Well, I'll even use an orange thing here. Well, c is 3. We wanted to eventually get the absolute value of x minus c is less than delta. This is the absolute value of x minus c. Therefore, this is going to be our delta. So we have arrived. We have done what we are looking for. We have found the formal connection that we need between these two. We're just going to choose epsilon over 2 to be our delta. Whatever that distance is we want to be away from our limit value in the y direction, we'll just let delta be half of it, and then we'll guarantee that we get the closeness in y that we are looking for. So let's see what this ends up looking like. So how do we prove this? Well, first we just literally say, here's my delta. You just kind of say, here it is, here's my homework. So that's exactly where I'll begin. We are going to say taken, Liam Neeson. No, I don't know. We're going to take epsilon over 2 to be delta. Formal connection here, that's what we're looking for. From there, then, what comes next? Then, the absolute value of x minus 3 is going to be less than epsilon over 2. We can multiply 2 over. We'll get 2 times the absolute value of x minus 3 is less than epsilon. From there, we can distribute the 2 in because of the fact that 2 is positive. So this is 2 times x minus 3's absolute value is less than epsilon. We can distribute it in, get 2x minus 6 is less than epsilon. And then finally, we can just separate this out in a very strategic way. 2x minus 5 minus 1 has an absolute value of less than epsilon. Well, good news, everybody. That's f of x. That's L. So we've just shown that the absolute value of f of x minus L is less than epsilon is the direct result of us choosing delta to be epsilon over 2. And given all of that, that basically finishes our problem. Based on this conclusion, we have finished the problem, and we can just state our conclusion. Therefore, that limit we were looking for, the limit as x goes to 3 of 2x minus 5, is indeed equal to 1. But because this was a formal proof, we can conclude it like a formal mathematical proof gets concluded by putting in QED, which stands for quote erat demonstratum, which means that which has been proven, which is just kind of the math flex you use to finish a proof. And that's what a epsilon-delta proof looks like. A little bit of work from us kind of starting at that conclusion we want of that like distance in the y direction being epsilon. We work back to find our delta related to epsilon, and then we just kind of reverse the whole process. It's kind of like here we're going down this way, and then over here in this case we're going downward, and then in this case it's sort of the reverse. Like we're going downward again, but it's backwards. So yeah, so there it is. We start there and go that way, and then to do the right side we go up. So yeah, there is your proof, and I need to take a break to fix my computer, and then I'll come back and talk about it a little bit more. So we just did our first epsilon-delta proof, but there's probably that lingering question in your mind of like, so what the heck did we just do? And so I want to just kind of use a quick graphing calculator demonstration to show you what it is that we just did. And I'm going to give you the most important thing. What we just did was establish a connection between epsilon and delta. What we said is if we choose delta to equal our epsilon over 2, that's going to allow us to be sufficiently close to the limit value in the y direction as we are in the x direction to c. So it's that formal connection. This is delta as a function of epsilon. We've connected those two closenesses, those two measures of closeness, which are just the distances from c and l respectively, delta and epsilon respectively. We've established that connection. And because these functions are linear, I can very easily show you what it is that we've accomplished here. So let me do exactly that with this graphing calculator. So what I'm going to do is I'm going to graph 2x minus 5. And no surprises here. 2x minus 5 is a line. There's no surprises, as I said. But what I want to show you is that our connection is actually valid. What is it that this connection delta equals epsilon over 2 says? Well, to do that, let's establish a connection in the y direction. So let's say this. Let's say we want to have an epsilon value of 3. What that means is we want to be within 3 units of the limit value, which in our case was 1, by the way, in the y direction. That's what we're aiming for. We want to be within 3 units of the limit value. So in other words, we want all of our y values to be in the interval 1 minus 3, 1 plus 3. In order to do that, according to what our connection says here, we need to take delta to be epsilon over 2. What that means is that in our x direction, we are going to be c minus delta, comma c plus delta. So let's see what that ends up being in this case. Well, c was 3, so this will be 3 minus epsilon over 2, and 3 plus epsilon over 2. So I submit that if we have our x values between 1.5 and what is that, 9.5 or 4.5, then all of our y values will be between -2 and 4. So let's see what it is that looks like on our calculator. And I'll do one more after this to kind of verify what's here. So notice, by the way, as we look at our window, we're not going like corner to corner here. We're not seeing all of the function. There's chunks over here that aren't there. Watch what happens when I set up this particular piece. For the x direction, I'm going to be 3 minus 3 halves for the minimum, and then 3 plus 3 halves for the maximum. Doesn't really matter what our x scale is. For the y, I want to do 1 minus 3, and then 1 plus 3. And again, what we're doing here is we are saying that if we're within 1.5 units of 3 in the x direction, our y values will all be within 3 units of the limit value, which is 1. And what that'll look like graphically is we will see on our graph the entire line's graph in the window. Like we'll literally go corner to corner. Watch it happen. Notice our graph goes from corner to corner. It works out perfectly. We're covering the entire function because we're sufficiently close to the x value, 3, to be within, 3 halves? We're sufficiently close to the x value 3 to be sufficiently close to the y value 1, the limit value. So that was just one potential epsilon value, though. What if you were like, no, I want to be much pickier. What if you want to be instead, you want to have an epsilon equal to 0.1. Like, oh shoot, what would that be? Well, if we want epsilon to be 0.1, then our y values, which again are supposed to be close to the limit value of 1, will be between 1 minus 0.1 and 1 plus 0.1. And I'm not going to simplify here just for simplicity. Likewise, if that's going to be true, according to our connection between delta and epsilon, all of our x values need to be within epsilon over 2 of our c value, which was 3. That means that our x value, which was at 3, will be between 3 minus 0.1 over 2 and 3 plus 0.1 over 2. And again, if this is true, if we have done this correctly and we have established the connection between delta and epsilon properly, when we graph this, our picture should look identical despite the fact that we're changing the intervals. Because what we're saying is that if we're this close to the x value we want, we're this close to the y value. So we should see all the values because we're sufficiently close. So once again, I'm going to go to my window. In this case, I'm going to change it now. I'm going to do 1 minus 0.1. Oh, no, sorry, this is x values. I apologize. Did this backwards. 3 minus 0.1 over 2. And then 3 plus 0.1 divided by 2. In the y direction, we're going to go 1 minus 0.1. And on the other one, 1 plus 0.1. And when I go to graph this, we should see the exact same shape, which I know is going to be sort of disappointing, but it's true. We have the exact same shape. Because of course we do. We have formally established a connection between the closeness to x and the closeness to y. We've found a valid relationship between delta and epsilon. If we just take our delta to be whatever that threshold epsilon is in the y direction divided by 2, we're going to always be close enough in both directions. So that is what epsilon-delta proofs do, or our work along that way does, is it formally shows there's a connection between delta and epsilon, so that we've formally established a connection between closeness in the horizontal direction and closeness in the vertical direction, and then we just go ahead and say, here's how it works. So there is sort of your, there's your sort of visual of what's actually happening here. So now as far as our plan, what it is we're going to do to attack this, it's exactly what we saw on that first page. Basically, we're going to do a little bit of work first to sort of establish the connection. We're going to basically go find the connection. Although with linear functions, you'll figure it out pretty fast. And then we'll just use that connection and go in the opposite direction to conclude that our function value is within epsilon of our limits value. So as it says, we begin with the work. By the way, it's in gray to kind of illustrate that idea of like it's like scratch work or a rough draft of something. Basically, you begin at stating the conclusion that we want, which is that the absolute value of f of x minus L is less than epsilon. Then you use algebra to arrive at the absolute value of x minus c is less than delta, the ultimate result we're looking for. Once you've got that, this thing will be your friend. You have delta as a function of epsilon, which is exactly what you're looking for. Now, start by saying, okay, well, let's just take this delta to be epsilon. Sort of, oh, where did that come from? Well, I don't know. Here's a possibility. Let's choose this as our delta. And then do all your work backwards until you conclude that the absolute value of f of x minus L is less than epsilon, which should be true because, remember, you started it there. You began that place. You began at that conclusion, so therefore you should be able to conclude it when you just reverse everything. And then finally, just state what your limits value is, and then finish by saying QED. So that way it really establishes that this is a formal proof. And this is a task that, if memory serves, I actually did in week 1 of my calculus class. At Davis, my calculus 1, I retook it all. Long story short, I retook the entire sequence there. And then also in my proofs class, my first upper division proofs class as a math major. So basically this is a thing that actually shows up at the college level. It's just not a part of the AP Calculus curriculum. Rightfully so, by the way. I think it's a little more abstract than necessary here as you're kind of getting into this stuff. But, hey, it's a topic that we've taught before and I want you to be comfortable with in case you run into it in the future. So let's do one more just to kind of illustrate this process and make sure you're comfortable with using that plan. So this time we're supposed to use epsilon and delta to prove that the limit as x approaches 8 of the line 1/2 x plus 7 is equal to 11. And again, you could use direct substitution and say this function's continuous because it's a polynomial and then conclude stuff that way, but that's not what we're being asked to do here. We are specifically supposed to use epsilon and delta, so that's what we're going to do. And just like last time, I'm going to sort of establish a set space for us to do our work in, and then we'll go forward and we'll actually do the proof. So we'll do work over here. Always nice to establish this is my workspace. This is my place to work. But whatever. As I said before, we're going to start by assuming that our result is true. Let's assume that the absolute value of f of x minus L is less than epsilon. Like, I don't know, let's just take a flyer on that idea. Well, in our particular case, here's f of x, here's L, and of course here's c. So looking over there, that'll be 1/2 x plus 7 minus 11 is less than epsilon. So starting there, now our job is to just sort of eventually get it down to the point where we can conclude that the absolute value of x minus c is less than some delta that's a function of epsilon. That's what we're trying to proceed towards, because that would allow us to sort of reverse the process and write our proof. So let's just start with kind of the simplifying stuff. This will be 1/2 x minus 4 is less than epsilon. From here, I'm going to do some like weird moves. You can probably anticipate where I'm going with all of this stuff. I'm sorry, why did I write 11? It's supposed to be 4. I literally said 4. 1/2 x minus 4. I want to eventually get down, by the way, to the absolute value of x minus 8 is less than something. So you can probably see where this is going to go next. I'll factor out a 1/2. That'll leave me the absolute value of 1/2 times the quantity x minus 8, all less than epsilon. Just like before, I can factor out that 1/2 because 1/2 is positive, so I can pull out the positive scalar from the absolute value function. And then from here, I'm going to multiply both sides by 2 to get rid of that 1/2. That will leave me with the absolute value of x minus 8 is less than 2 times epsilon. And that's what we were looking for. Let's just choose this to be our delta as a function of epsilon. So basically there is sort of our grand piece. If we let delta be twice epsilon, that should unravel back into our limit being sufficiently close, or within epsilon specifically, of our function value, or our limit value. So based on that, we can now go over to the other side and actually start to attack it. So we'll establish that this is a proof by writing proof. I remember in college many times I just wrote proof. But like, why? I can do better than that. Why not write proof? We don't get to do many proofs. Let's just establish it right there. So we're going to do a proof. We're going to start by telling you where to start. Like, what is my delta that I want? Well, let's just take delta to equal to epsilon. So whatever epsilon is, double it. Double or nothing, buddy. Okay. If that's true, then we can start to make our connection. Then the absolute value of x minus c less than delta is the same thing as the absolute value of x minus 8 is less than 2 epsilon. That's specific to our problem. From here, I'm going to multiply both sides by 1/2. So I'll say that 1/2 the absolute value of x minus 8 is less than epsilon. I'll distribute that in because it's positive. I'm allowed to do that. This will be the absolute value of 1/2 x minus 8 is less than epsilon, or minus 4. Geez, I keep messing up that constant when I write it. That's a constant problem, I tell you what. From here, I'm very speculatively, I'm just a clever boy. I'm going to do 1/2 x, and then I'm going to do, I don't know, plus 7 minus 11 maybe? Like, I don't know, how about that? Let's go with that. And look at that, that's our function. We've just shown that effectively the absolute value of f of x minus L is less than epsilon. And yeah, I didn't formally state that those are the same things, but I'll go ahead and forgive that here. This was really our conclusion step. We got where we wanted it to. Based on that, we can conclude our proof by restating our limit. The limit as x goes to 8 of that line 1/2 x plus 7 is going to be equal to 11. And we have used a formal epsilon-delta proof to establish a rigorous and precise connection between closeness in the x direction, which was delta, also known as 2 epsilon, and closeness in the y direction, which is epsilon itself, which results naturally from our choice of 2 epsilon. So there we go. And before I move on to the next page and do one that kind of twists it just a little bit, if you're looking at this going, oh, for the line mx plus b, delta is always going to be epsilon over m. Yeah. I still want you to do this. Like if I was grading you, like this isn't going to probably show up in the next few years. But like I'd still want to see the work in your stuff. But yeah, it's no coincidence that this is your connection. That's true. That is what's happening every single time here because of how we're setting this up. So just FYI. The last little piece specific to sort of the basic epsilon-delta proof that, if I remember right, showed up on my exam at Davis, it showed up on my exam in high school, and it was almost always what our exam question was on tests in this course, or in AP Calculus AB when we taught it. It almost always, this was the other wrinkle that was there. Basically, instead of just looking for you to prove a formal connection between the two, basically defining delta as a function of epsilon, we give you an epsilon and say, okay, I want you to be within this close or this much, this distance of our limit value, huh? What's the delta now? And yeah, it's not going to be that difficult. We just have to do the same general process to get there. So let's take a look at what we got. we're going to say we're going to let f of x be 3 minus 4x. So again, it's a line. We're keeping things linear here until the last example I'll do in a second. And then, of course, they're defining the limit as x approaches 3 of 3 minus 4x equal to L. And in this case, I want to go ahead and just like quickly grab that limit value. Let's just make sure we have it because it's not given to us. So what is the limit as x goes to 3 of 3 minus 4x? Well, yeah, this isn't exactly the hardest calculus problem you're ever going to get. That's 3 minus 12, also known as negative 9. So basically that is going to be our L value. So it's just nice to have that sort of established for us. Cool. Now what's different here? Well, it asks us to find a positive delta such that the absolute value of f of x minus L is less than 1 over 100. So basically this is sort of our new ingredient here. They have established for us that epsilon, the epsilon we want, how close we want to be to the limiting value, is 1/100th, or 0.01 if you so desire. So we have a specific goal here. What we want at the very end, in this case, our goal is to actually get a specific delta, which is equal to some number. We want to get a real number delta that says if we're this close in the x direction, we'll be within 1 over 100 of the y value. Like, that's a pretty classic thing. Like, that's how accurate do you want to be? It's sort of a practical question of, what is it, quality control. I think this is almost a precision question. It's very explicitly so. So how can we do that? Well, basically, we're just going to do the problem like normal, figure out what the connection is between delta and epsilon. So basically the work part of our proof, and then we'll just plug in the specific epsilon. It's actually easier than the work that we were doing before. So let's see what that would be. And again, I'll even sort of establish it. We're looking at the work side. Well, okay, what is that going to be? Well, we want to start with the absolute value of f of x minus L is less than epsilon. And I suppose there's an argument to be made that you could just plug in 1 over 100 at the beginning, but I'm not going to play it that way. I'd rather keep this general so that way if there are multiple different things, you wouldn't have to do it multiple times. So we'll start there. Looking at my stuff, this will be 3 minus 4x minus our L value, which we saw to be negative 9. So that'll be minus a negative 9. That all needs to be less than L, or less than epsilon, not L. I took the L in that one. So from here, I'll clean this up a little bit. This will be minus the negative 9, so plus 9 plus 3 is 12. So the absolute value of 12 minus 4x is going to be less than epsilon. Well, in absolute value, it doesn't matter what order you subtract because the result is always positive. So I'm just going to go ahead and take advantage of this. I'm going to write this as, I guess I can do it this way. Let's do it this way then. I was going to say I didn't do it this way normally. I normally just use that result, but I think this will be a little bit clearer for people. This will then be, if we factor out a GCF and negative 4 on the inside, the absolute value of negative 4 times x minus 3 is less than epsilon. But because of the absolute value of negative 4, which we could literally write this as the product of two absolute values, maybe that's helpful to you to see as well, that is just going to be 4 times the absolute value of x minus 3 is less than epsilon. And now that we've established that connection, we can divide both sides by 4, and we'll get the absolute value, it's a terrible absolute value line, the absolute value of x minus 3 is less than epsilon over 4. And at this point, we have arrived. This is our delta, because this is now the absolute value of x minus c. So based on that, we now know our connection. Whatever epsilon you want, I just got to divide it by 4, and that'll give me my delta. That'll tell me how close I need to be in the x direction to be sufficiently close with an epsilon of the y actual value, or of your limit value. So in here, cool. If epsilon is equal to 1 over 100, which we established it is, then that means that delta is going to be equal to 1 over 100 divided by 4. And I mean, you could just write that, that's fine. But of course, I'd rather just write it as 1 over 400. So basically, if we want to be within 1/100th of the limit value in the y direction, we need to be within 1/400th of x equals 3 in the x direction. And there's our stuff. We have our stuff. We actually found the specific value we are looking for. And of course, if you wanted to graph this, I don't want to do that just for the sake of timing. If you wanted to graph this on your graphing calculator and actually check, like, what would it be? 3 plus 4, 1 over 400, 3 minus 1 over 400, and then, of course, the limit value, negative 9 plus or minus 1 over 100, you'd see that we do, in fact, get the entire line, just like we talked about before. So there is sort of the one like major wrinkle that kind of pops in with the basic epsilon delta question is like, I'll give you a concrete epsilon. you find me the concrete delta that connects those two and establishes the closeness we're looking for. Now, I do have one problem left, but it's not the classic linear question that typically shows up. I think you've seen all the varieties of the questions that we would ask on an actual exam if we were teaching Epsilon-Delta, and the types of questions that for the most part would appear on sort of a foundational level Calculus 1 class at the university level. I think you've sort of seen what's there. So before I go on to the last problem, which sort of does its own thing, let me just sort of go over a quick little paragraph here that I think summarizes what it is that's happening with this whole Epsilon-Delta ballgame we're talking about here. It says, and I wrote this in, I believe, 2013. It felt like one of those things where I wrote it down. Maybe it was 2015. It was with Christine. Whatever the case was. It was either with one of two people. Regardless, this just sort of summarizes the idea of what we're looking for. Although I think I've already put it into words better than I ever have before. Weirdly enough. It's been like 7-8 years. So it says, the definition states that for every epsilon greater than 0, there exists a delta greater than 0. And so that is basically our beginning. We're trying to establish that this is an existence proof, by the way. We're trying to show that there is such a delta that exists to establish this connection. By finding delta as a function of epsilon, we can show that any epsilon we pick has a corresponding delta. In a sense, what we saw in the previous problem was that for a specific epsilon, we could find the corresponding delta. Earlier, when we actually did this, we were finding formally that connection. We're saying, well, it doesn't matter what epsilon you pick. If we just pick, in this case, I think it was delta as epsilon over 2, we establish that connection. So we're trying to connect those two things together when we do the process. So any epsilon we pick has a corresponding delta, since that epsilon can be plugged into delta as a function of epsilon. It's that formal connection. It's that delta as a function of epsilon that is that connection we're looking for. Therefore, we have formally connected closeness in y to closeness in x, so that, and I think the green thing does a nice job of kind of wrapping it up, being within delta of x equals c means we'll be within epsilon of f of x equals L. So in other words, we've established the connection. If you want to be this close to your limit value, you got to be this close to your x value. And if I could just sort of distill, if I could make a Epsilon-Delta explanation extract out of something, it'd be that last phrase. If you want to be this close to your limit value in the y direction, you got to be this close in the x direction to x equals c. That is the essence of Epsilon-Delta limit proofs, which is kind of cool. And that would be the end of the lesson, if not for the fact that I am a glutton for punishment, and I really want to do one of these quadratic ones, because that is the most exotic thing that I've ever run into beyond what you've already seen. It's the only thing that's there. Our old textbook used to include an example in the explanation, and I've been studying this all morning today, just trying to make sure I've got the language for it. So in a sense, it's kind of a test for myself. If it doesn't work, I'll just come back and do it again until I get it. So I think you're going to get a good explanation no matter what. It just might be darker in my room when you actually get there. We'll find out. So our last question asks us to do effectively the exact same thing. We want to find a particular delta so that we can be connected, or we can connect that closeness in y to closeness in x. The difference is we're not using a line anymore. Now we're using a quadratic function. We want to show that the limit as x approaches 2 of 4x squared minus 3 is equal to 13. And that's just a different ballgame than what we were doing before. So to honor that fact, I'm going to take a second here and establish our two pieces. And this is definitely weirder. There's some weirdness in here, and you can probably anticipate why if you think about what our process looked like. It's basically going to have to do with the fact that we're going to get two linear factors here, not just that one single one that immediately matches x minus c. So let's just go about it and see where we end up at, because I think you'll start to feel this out as we go through. And by the way, this is one of those things where I feel comfortable doing it far more than I do feel comfortable saying it. So like I said in the previous page, this is a challenge for me. So first of all, our work. Where do we want to begin? We always want to begin at the absolute value of f of x minus L is less than epsilon. And you can sort of see what's up here. There's f of x, there's L, there's c. Say hi, everybody. There it is. Okay, now, I can set up that first line without much trouble. This is 4x squared minus 3 minus 13 needs to be less than epsilon. That's totally cool. I can also establish that this is 4x squared minus 16 is less than epsilon. And in fact, I'm just going to go ahead and write one more line here. I can pull out a 4 And as you can probably anticipate, pull that 4 out, we'll get 4 times the absolute value of x squared minus 4 is less than epsilon. So already you can start to get a feel for some of what's here. On the one hand, on the left side, we're just going to have, if we divide by 4, we're just going to have the absolute value of x squared minus 4, which I hope you're okay factoring into absolute value of x plus 2 times absolute value of x minus 2. On the other side, we'll have that epsilon over 4. So, cool stuff. This is really good, but unfortunately, this is sort of our inflection point. And the inflection point is caused because, as you can tell, with c being equal to 2, we want to get x minus 2 less than something, but we have this value still sitting here. This is the issue we're dealing with. What are we doing with absolute value of x plus 2? Where does that go? How do we get rid of it? What happens with it? And that's what I'm going to show you. That's why I've switched the colors here a little bit. There's a chance we may even need the other page in order to make this work. So what we're going to do in this case is we are going to pick a delta. We're just going to pick arbitrarily a delta, although my recommendation is always to choose one that's easy to work with. Basically, we're going to contribute a potential delta into the problem. And that does mean there are an infinite number of these proofs that are out there, depending on what you choose. If you chose delta equal to 4,686, well, you're going to have a miserable time doing the rest of the problem, but technically that's perfectly valid as well. I'm instead going to pick my delta to be the cleanest, simplest number I can, that again is positive. It is positive. I'm going to pick delta equals 1. And I'm going to explore what happens if I choose delta equals 1. So thinking about that, if delta equals 1, which is a thing that can happen, then we end up with the fact that our x values, again, we know that absolute value of x minus 2 has to be less than that delta. And what that tells us, if we just kind of think about this, is that x minus 2 has to be between -1 and 1. And then if we add 2 to both sides, we're going to show that x has to be between 1 and 3. Now, what has that done? Well, it's just given us a bound for x. But there's a reason that a bound for x is super valuable. It's because we have this x plus 2 factor we're trying to deal with over here. So let's go deal with x plus 2. If x is between 1 and 3, which again came from our arbitrary choice of delta being 1. We could have chosen delta equals 10. I just chose 1 for simplicity. If 1 is less than x is less than 3, then that's the same thing as saying x plus 2 has to be between 3 plus 2 and 1 plus 2, because we're just adding 2 to everything. In other words, x plus 2 is between 3 and 5. So again, what we're doing here is we're bounding that extra factor that's sort of interfering with us getting to the absolute value of x minus c is less than delta. So there's what we got. That's going to be true. So if that's true, that implies something else that's sort of helpful. It implies that the absolute value of x plus 2 is always going to be less than the biggest of those two values, right? So the absolute value of x plus 2 is going to be less than 5. If you're like, wait, what happened to the 3? Well, the 3 is smaller. So we just know for sure that x plus 2 is always going to be less than 5. That just has to be true based on what we always had. So therefore, we have found a way to bound that extra factor that's sitting over in our work. So if we go back to this line that we had, and I think it's going to let me copy it. Heck yeah. So based on that, we can return to this point, and we can replace the absolute value of x plus 2 with 5. Right? That makes sense, because of course it's always going to be less than 5. So based on that fact, we can go over here and say, okay, cool. If that's less than or equal to 5, this is always going to be true. We can divide that over, and we're going to end up with the absolute value of x minus 2, which is, by the way, the absolute value of x minus c, the thing we wanted. That's going to be less than epsilon over 4 divided by 5, which is epsilon over 20. And this will be our delta, sorta. So we now have, by the way, a formal connection between delta and epsilon. We can choose delta to be equal to epsilon over 20. That works out great. But there's a problem here. And you probably caught it and felt it like as I did it. You were probably like, wait, why did you do that? How can you do that? And it all comes back to right here. this is the most uncomfortable portion of the work that we're doing, of this entire like quadratic proof, is I chose delta to be 1. Like, what if I'd chosen delta to be 42? What if I'd chosen delta to be 13 or pi or 1/7? There was an infinite number of possibilities, an uncountably infinite number, because any real positive number would have worked. So it's like we have delta equals 1, but then we also have delta equals epsilon over 20. And it's like, well, how do we do that? Like, that's two different choices. Like, what if they're different? Like, how can we guarantee we're close enough when you have two different deltas? And by the way, just as a heads up, you've actually kind of seen this come into play when I did that demonstration of that graph earlier. And someone probably would have objected and gone, wait, that epsilon is much closer, or that L minus epsilon, like that's much closer than this side is. And the answer is, yeah, you're totally right, it is, because of the curve that's there. There's that concave upness, or that concavity that's sort of playing a role in this. So for us, what we have to do is we have to do something very specific with our deltas. We want to make sure that we are sufficiently close, and we sort of have two possibilities, 1 or epsilon over 20. How do we guarantee that we have the closest we need to be, or as close as we need to be? There we go. How do we guarantee that we are as close as we need to be? Well, when we go to do our proof, we're just going to make sure we choose the one that's closest. In other words, when we do our taking of delta, take delta. No, you take delta. When we take our delta, we're going to let delta be the smaller of those two. So the way that looks formally is you'll say let delta be the minimum of, and it'll be the minimum of two different things. It'll be the minimum of 1 and epsilon over 20. And what that does is it guarantees that we are close enough in this case. It guarantees that we are within the value that we actually need. So looking in this case, like what does that do? Well, in a sense, it forces us to have sort of the right relationship for what we're looking at. Based on that, if we establish that to be true, then the absolute value of x minus, and let's say 2, being less than delta, is going to be the exact same thing as being the smaller of those two. So what I'm going to do then is I'm going to point out that that means that the absolute value of x minus 2 is going to be less than, and I'm going to choose to do epsilon over 20. Of course, if it wasn't epsilon over 20, then we'd have the possibility that it was less than 1, and then it would still be less than epsilon over 20. If we did it in reverse, it would still be true. Basically, we'd still be below epsilon over 20, so I'm just going to go with that as my piece. I'm going to choose to let it be the case. Now that I have it, I've got to start unraveling all of those pieces that I have here in order to get what we're looking for. So specifically, I'm going to first write that epsilon over 20 as 1/5 times epsilon over 4, and then I will multiply by 5 on both sides. In other words, 5 times the absolute value of x minus 2 is going to be less than epsilon over 4. Now, based on that, this is also bigger than the absolute value of, and I need to kind of shift this over, sorry, I didn't space that thing very well. It's my first time narrating one of these. 5 is bigger than the absolute value of x plus 2. So we can say the absolute value of x plus 2 times the absolute value of x minus 2 is less than 5 times the absolute value of x minus 2. And that, of course, is less than the absolute value of x minus 4, or x over 4. From there, I'm just going to drop this middle section because this is clearly smaller as well. So when I do, I can transform this into the absolute value of x squared minus 4. I can then say that's less than epsilon over 4. I can multiply the 4 over and get 4 times the absolute value of x squared minus 4, which is going to become the absolute value of 4x squared minus 16, being less than epsilon. And then I can clean that up just a little bit further in here. Absolute value of 4x squared minus 3, all minus 13, is going to be less than epsilon. And that establishes our function minus its limit. The distance from our limit to our function values is always less than epsilon, which is what we were shooting for in the first place. So based on this, we've made our connection. We've got everything that's there. It's good to go. And we can therefore state that our limit as x approaches, 2, of 4x squared minus 3 is equal to 13. And I'll just finish that off with a quick little QED. So there we go. So in this case, too, we've gotten our limit proven. Like, we've got everything there. Everything is correct. I do want to address the one situation here that I have a feeling would give people sort of problems. Like, if there was someone in front of me, they would totally ask about this line. It's like, wait a second. Whoa, whoa, whoa. How could you do that? And it all comes back to this little piece. So give me a second. I'm going to steal this and go to the next page and just really quickly talk about those choices. So here we go. So we're doing this proof, and we're trying to address the idea that we can choose either of these options and still end up with the exact same proof, because we've said delta is the smaller of the two. So consider it this way. We obviously want to do the absolute value of x minus 2 is less than delta. So first of all, we have two cases at this point. And this is another one of those situations I've never said out loud before. I've just thought it a lot. So our first case, case 1. If 1 is less... Actually, let's do it the other way. If epsilon over 20 is less than 1. So what happens if that's true? Well, based on that, that would imply that delta is going to be the smaller of those two, so delta equals epsilon over 20. Based on that, we would do exactly what we did from before. It would work out exactly that same way that we did, every step following through, just like the previous page. We already did that. Been there, done that. So that is our first piece. That first page, like what I wrote in our proof here, sort of made the assumption that epsilon over 20 was smaller. So that was sort of case 1. The question, though, of course, is, well, what happens if that's not true? What if, in our situation here, the minimum of those two, what if 1 is less than epsilon over 20? Because wouldn't that cause changes, since that would mean delta is equal to 1? It does, but not for the reasons you're thinking of. What that tells us is that choosing x minus 2 less than delta would be choosing that absolute value of x minus 2 is less than 1. But because 1, I'm just going to literally underline it, it's super cool. Because 1 is less than epsilon over 20, we can just conclude that, well, that's true as well. In order to be less than 1, you're also less than epsilon over 20, which means you could just sort of go back and go, okay, just kidding. Let's let absolute value of x minus 2 be less than epsilon over 20. And then from there, every single thing follows the same model we did from the previous page. So the idea is we jump right to the epsilon part because it doesn't matter which one's smaller. We still have the same established connection. We can still formally connect epsilon to the closeness we want in the x direction, and we end up exactly where we're looking for. So this proof is valid. There's just sort of this hidden assumption that I've never actually seen written by anybody. Like in instruction when I was in college, in high school, online, I've never seen anyone state these cases, but this is the implication of what's happening. So actually, I think I've contributed something nice to the zeitgeist. So I'm happy with that. Also, what I'm happy with is this is the final lesson of any lesson that Ms. Formaker and I and Mr. Nickerson have ever taught in AP Calculus AB or BC at Franklin High School. So effectively, that's all, folks. Dun-dun-dun-dun-dun-dun-dun. But that's it. I was going to say I have some information here about epsilon m proofs, but that's not Epsilon-Delta. And that's not something that I want to go through and explain to you. I don't think it's rich. And hey, if you take that Calculus 1 class and you need it, just let me know and I'll make a video for it. For now, though, instead, we have now done sort of the most intimidating and abstract thing in all of calculus, at least at the Calculus 1 and 2, the single variable calculus. We've learned how to prove epsilon-delta proofs for limit values. So we started with what we were doing. We made some connections and graphs to kind of explain it. We did a few proofs and established what was happening in that case. We learned the plan and did it once. We learned how to establish, if we're given an exact epsilon, what to do. And then finally, we looked at even a quadratic case, which, by the way, you can generalize this to cubic cases and other polynomial ones. If it's not that kind, it becomes a little bit trippier. Again, I've never seen one of those done, so I can't show you exactly what they look like, although I bet I could find a friend that actually can and has encountered it more often, that took more real analysis than I did. But all I care is we are finished. That's going to conclude the lesson. Thank you for watching. I hope this was a valuable experience for you if you're looking into this. And yeah, have a great day wherever you are. Honestly, whenever you are. For me, it's July 2nd, 2023. Who knows where you are in life? I know where I am. I'm going to bed. Thanks, everybody.